So, Steve, we are very happy you are again with us.
Right.
It's
Very happy
always
to be here.
it's always a pleasure to have you with your interesting talks. I would like to ask you because I explained to you a little bit about the film. So I would like to ask you first in with a few words to tell us what are the highlights of your talk.
Right. So the main idea of the stuff I'm doing at the moment is to use string theory, which is one of the few theories we have which can treat everything at all scales consistently. And we're trying to use that to understand some of the most fundamental problems about the Higgs, in particular how it's getting its mass, how its mass is protected from the rest of the theory. And so we found that you can do some quite general fundamental things just based on the structure of the theory, and you can understand some fundamental things about how a Higgs should behave that way without going into the details of model building and that sort of thing. So that's the excitement for me. It sort of feels like it's an equivalent to where particle physics was when people first wrote down a potential for particle physics, essentially.
No, it was very interesting talk actually. Thank you. Now, since you have been here and you know our activities since over years, and even now you have seen what we are doing, and what is your, in general, what is your impression about our tries here?
So this is one of my favourite places to come, I have to say, just because of the atmosphere and the location and everything. And so I mean, it could really become something, an important and interesting centre for people to come and visit.
When we
kind of like
when we renovate also the buildings,
yeah,
and things like that.
So if it could become like an Aspen or something where people can
this
come
was
and work
originally
together
the
for
idea,
a long time, that
this
would
was,
really be
Aspen
something.
was one of our ideas, and
yeah, I mean that would be great. I would come the whole summer.
Yeah, and the final question is, since we have so many young people around, what will be your suggestion? They are in the beginning of their career or of their research attempts.
Yeah.
What is your suggestion to them?
Oh, I mean, to stick with it. It's an interesting field, and it takes you into lots of other directions. So you're not, you certainly don't lose by joining this field, and it's one of the most exciting, and interesting fields. Okay, right. So thank you very much for the invitation to be here. I can't tell you how nice it is to be coming to an actual in-person meeting nowadays, and especially here, which I always like to come to. So I'm going to talk about some work I've done with Keith Denes about understanding the Higgs mass, but from a string theory viewpoint. So we are not really in the business of model building or anything like that. We just want to understand what happens to something like a Higgs mass in a UV complete theory. So this is our motivation. Of course, you're all very familiar with it, but I'm going to recap it anyway. As you know, the Higgs is one of the least well-behaved fields in the standard model. And the way that you can see it, one way you can see it is to construct its effective potential. So I've just taken this directly from Kolb and Weinberg's paper. You write all of your diagrams like that, and you find that when you find the potential, so I'm going to refer to it as the cosmological constant, the potential. When I write the potential, you find that you need cutoffs, and you have a quadratic dependence on the cutoff there, which is a leading term, and it's proportional to then the super trace of the mass squareds in the spectrum. And then also you have a logarithmic term, which is indicating that when I take its derivative, it's going to tell me that the Higgs mass is going to be running as well. So not only is the Higgs UV sensitive maximally, but it's also sensitive to the infrared of the theory. So it's the canary in the coal mine. I don't know if this expression is used in other countries or if Britain was the cruelest country. What's that? Oh, so this is a coal miner. This is a canary, and you would take the canary down with the intention that it's the first thing to die if there's a problem, rather than you. So that's the role of the Higgs. The Higgs dies first, basically. So we're interested in looking at what happens in a full theory, in a string theory. And our sort of starting position is that if you assume that nature is based on a closed string theory, whatever it is that makes the theory finite has to be there even today. And the thing which makes string theory finite is not supersymmetry, but modular invariance. So modular invariance is the thing which, and I'll show you how, renders all the diagrams finite in quotation marks. So it's finite up to infrared divergences. In most string phenomenology, you don't really think like that. What you do is at the beginning, you begin with something like a supersymmetry, and then you'll jump to the effective field theory, and you'll throw away at that point modular invariance. Most of string phenomenology will do that. So you're kind of abandoning the beautiful thing which was at work making it all finite, and so you kind of lose any potential lessons that you might be able to learn. As I said, if you assume that the universe is based on a closed string theory, the world today is still operating with that symmetry underlying, so it has to still be finite. So there should still be modular invariance in the theory. And then the question is, what does it tell us? What does that modular invariance tell us about, in particular, the effective potential? And a sort of related question is, as we'll find out, string theory is heavily UV-IR mixed, sort of maximally mixed. And so it's not obvious how an effective field theory emerges. I can pull it out by hand, but when I do it, I break modular invariance. So, it's game over, basically. So I'm going to, this statement is relatively controversial, but I think it's correct. No one, as far as I can see, has written down an equivalent of the Coleman-Weinberg potential for string theory. So that is, tell me what the potential should look like in terms of its mass spectrum. I don't want to know what the model is that you're interested in. I just want to know what it looks like in terms of masses M. And as far as I know, no one has done that. So that was our objective, and that's what I'll show you at the end. And my objective really is, I don't want to focus on any particular model. I just want to say something general for modular invariant theories. Right, so it'll take a little bit of explanation how we get there, because there are some, so I mentioned number theory. It's not something that we physicists tend to carry around in our heads very much, number theory. So I'll have to explain a few things on the way. And so it's a little bit of a trail. So do try and keep up, and I'll try and complete the trail in 30 minutes. So there are three parts to the talk. So first of all, I'll talk about the effective potential of field theory, but I'll write it for you in a very stringy way. And then I'll show you what happens in string theory then, which will look hopefully moderately familiar by that point. And I'll show you how modular invariance affects the answer that you get. And then finally, I'll talk about renormalization, which is something we'll have to get to. Right, so this is going to probably be less familiar to you, which is that integral I can actually write as a supertrace over the entire spectrum. And this is an identity which you can prove. And it's a kind of very number theoretical thing. So lambda, it can be written like that. The supertrace is now over the entire infinite spectrum of the theory, whatever it happens to be. So I don't need to tell you what model it is. As long as the theory is modular invariant, I can write the lambda integral like that. I can write lambda like that. So the mass squared that you get
for your state. Now, so it has the original thing, so it has the cosmodular constant. So this is the modular anomaly cancelling term. And then everything else I can write as a double derivative of something which I can call lambda hat. A lambda hat is a regulated lambda. So that is as if I took the original cosmodular constant, and even though it's finite, I decide to regulate that as well at the same scale mu. So I remove all of the light modes from that as well below mu, and I take its double derivative. That gives me the answer, right? So actually, initially, when we were doing this, we were starting by doing 2-point functions and so on, and then we just realized, okay, the answer at the end is really just a double derivative of a function that looks like that. What I'm showing you is it's an approximation to the actual result. The actual result is an infinite sum of Bessel functions. So it's a kind of complicated looking thing, which is a trace over the masses, over functions of masses. But it approximates very well to this. So you see that when you have any state which is lighter than mu, it will contribute something to this potential, which looks as if it ran up from its mass, right? So it contributes a logarithm. As long as the Higgs couples to it, it contributes a logarithm as if it ran up to the scale mu from its mass m. As soon as mu goes above its mass, it's exponentially squashed and it doesn't contribute at all. So you get something that looks like a running effective theory. And where it runs to is the answer that you would get for lambda if I didn't regulate it at all. So in the infrared, the potential it runs to the answer, the naive answer, if I don't regulate it. This result and the infinite sum of Bessel functions, which this margin is not large enough to display. So the infinite sum of Bessel functions is a fully complete effective potential, UV complete effective potential, and all it depends on is that the theory is modular invariant. It just depends on modular invariance. And it does everything that you need it to do. So below the mass of states, they fall out of the running. But when they're in the effective theory, then they will contribute as if they were running logarithmically up from their mass. And by construction, when we put in our regulator, everything is symmetric. So you end up with this sort of diagram. This, what I'm showing here on this axis is the energy scale. The most UV possible is mu equals m string, which is kind of in the middle. So remember, we had mu goes to m string squared over mu as a symmetry. So everything reflects around there. So what happens is, in the deep infrared, I asymptote to the unquenched answer. All right, I asymptote the unquenched answer. As I start to rise above, the energy scale goes above the scale of masses, things start to run logarithmically. As I reach the string scale, it has to somehow turn over and then do the opposite thing on this side. Of course, at this side, this is the ultraviolet. So we're no longer really dealing with anything like an effective field theory. It's just going to be, from our low scale point of view, it's at this end of things, what we're talking about is going to be quite a mess. But everything here behaves exactly as it would in the kind of naive effective field theory in these regions between the string scale and the infrared where things freeze out. Right, okay, so let me conclude. In this talk, I was talking about a general supertrace formula for the Higgs. In order to derive an effective potential which plays the same role as the particle effective potential that you all know and love. And so that is something that's written only in terms of the mass spectrum. Right? So regardless of what the model is, if your theory is modular invariant, its potential will be doing something like that. This modular invariant regulator of John and friends is very clever. And so we're able to adapt it, and we're going to insert a Wilsonian cutoff using it, and get a good definition of renormalization scale, even though the theory is completely UVI or mixed, and so it looks like it's quite problematic to do that. One thing that you probably noticed is the full potential, it looks kind of like the sum of an infinite tower of particle potentials. So that's one way to think of what's going on. And then something else, okay, well, let me skip to the end because I'm running over a bit. But I think we think it should be relevant for many phenomenology ideas. So, for example, you may be familiar with this naturalness condition of Veltman, which is that this quadratic divergence should be zero. In the string theory, you get an equivalent, but it's not the supertrace over the effective theory, it's the full theory. So the full supertrace of the full UV complete theory is the thing that should be zero, if you're going to believe that. Anyway, I'll leave it. Oh, yeah, it's small. Must be small.
The first question is what you are going to present, the highlights, let's say. The time is very short anyway, so in few words, how you will describe the main points of your talk.
The science I do tries to relate the physics of the very large, cosmology, the universe, with physics of the very small, high-energy physics. And high-energy physics is really the focus of this meeting. But we can learn a lot about high-energy physics from studying the universe. In particular, the Big Bang had energies and temperatures and pressures that we yet cannot produce on Earth, even at the wonderful accelerator at CERN. So my work has been trying to understand what went on in the primordial soup of the Big Bang and use this as an accelerator to try to understand high-energy physics. And in my talk, I will talk about one aspect of that. That is what happened during a very early phase of the universe and how this shed lights on what's possible in building models of gravity and how to get gravity part of the standard model of particle physics.
Very good. So you will give hints to the gravity part of the standard model.
That's right. That's right. So uniting gravity with the standard model of particle physics is really the work for the 21st century.
It's clear it's clear for the future. There are ideas, but we are far from establishing the standard model of the whole unification. That's clear. And although you are a few days only here, what is your impression of what we try to do here?
Well, one of the wonderful aspects of this meeting is the blending of senior scientists with young physicists, people just starting in their career. And it gives them an opportunity to interact with the senior physicists, to speak with them, and to present some of the work that they've done. And it's so important to expose younger scientists to the senior people, to give them the idea that the senior people do not have all of the answers, and there's plenty for them to do in their career.
It is true that we give opportunities to, of course, we choose the young people, they're not just the average, but it's very true what you say. And this brings us to the final question. What you would advise these young researchers whom you see around? I mean, is it a good direction to what they have chosen so far?
Well, I think a life doing physics is a wonderful life for me. Probably not for everyone. Occasionally, young scientists will come to me and say, what should I do? What sort of problem should I work on to try to advance my career, to get a job, and things like that. And my advice to them is do what makes your heart beat faster. Unless you really enjoy doing science, unless you really enjoy doing physics, then probably you shouldn't do it. And because it's not easy for me, I don't think it's easy for very many people, it's a difficult undertaking. And unless you really feel energized, unless it makes your heart beat faster to do it, then maybe you should look to do something else. And in choosing the problems that you work on, trying to predict what will be an important paper for the future, I think is impossible to do. And again, do what makes your heart beat faster.
Okay, so I'm very happy to be here. This is my first in-person conference since BC, before COVID. So I'm very happy to be around with the friends and learning things here. So the title of the talk is The Gravitino Swampland Conjecture. And let me say a word about swampland. It's typically thought that if an effective field theory is in the swampland, it's bad because people think that swamps are really terrible. Now, I don't know if you have swamps in Greece. I don't think so, but next. Okay, got it. I was born and grew up in Louisiana when there are not hurricanes, or even when there are hurricanes, there are swamps. And let me say a couple of nice words about swamps. Swamps, I think, have a beauty of their own, in spite of the fact that the animals who live there will either sting, bite, or eat you. So if you stay away from those animals, the swamp is actually pretty nice. So my talk today is based upon two papers. That were written with my collaborators, Andrew Long and Evan McDonald. Andrew Long is a faculty member at Rice University in Houston, and Evan has just taken a faculty position at the University of Winnipeg, which I believe is very close to Canada. And there are two papers, one of Long Phys Rev D paper and another a Phys Rev letter with the title Gravitino Swampland Conjecture. They may have appeared already. I don't know. You know, we've gone through proofs and things like that. So they will soon be published. And there will be a few more papers on the way. So let me say a word about the type of work that I like to do. Okay, good. Thank you. So, good. Now let's go on one more. Great. The connection between high energy physics, sometimes known as inner space, and cosmology, often referred to as outer space, is a symbiotic relationship. What we learn from high energy physics gives us information about the cosmic microwave background fluctuations, large scale structure, etc. And what we learn about cosmology can limit particle properties and limit model building in high energy physics. All right, so cosmology gives potential insight to high energy scales and potential insight to theorists for model building, grand unified theory, SUSY, supergravity, etc. And again, high energy physics gives us information to try to understand the evolution of the universe. And today I'm going to use an aspect of what happens in the early universe, namely that the expansion of the universe lifts particles from the vacuum, and this is known as gravitational particle production. So there are two ways that you might imagine producing new particles. One is the brutish way of smashing things together. That's what they do at the LHC. Or the refined way of using the expansion of the universe to produce new particles and study what happens. All right, so this scalar field theory gives us a simple example about how this might work. So let's couple a scalar field phi to gravity, and the coupling to gravity has something that's unknown that you can add as a dimension 4 operator involving the Ricci scalar r, and with some coefficient c. If c is equal to 1/6, it's known as conformally coupled, and if c is equal to 0, it's minimally coupled. So working in conformal time related to the scale factor, A is the FRW scale factor, the mode functions satisfy a wave equation. And the only unfamiliar thing about the simple wave equation is a time dependence to the scale factor and a possible time dependence to the Ricci curvature. So if you start with the wave equation, you can, in general, write it as positive and negative frequency terms in chi. The positive frequency term is proportional to alpha. And then the wave equations for A and B, alpha and beta, are listed there. And you see that an initial condition would be alpha k equal to 1 and beta k equal to, that should be 0. I'm sorry, initial conditions of beta k equal to 0. And a pure outgoing positive frequency solution would be a good solution if it is an adiabatic expansion. And there is a parameter that can be defined that tells you how non-adiabatic the expansion is, and that is the derivative of the derivative of omega divided by omega squared. If that is much less than 1, then the expansion is adiabatic, and particle creation will not be efficient. However, if the adiabaticity parameter is larger or comparable to 1, then you will be efficient at creating particles just by the expansion of the universe. So abrupt changes in the scale factor as a function of conformal time leads to non-adiabatic changes in omega, which adulterates, in the words of Schrodinger, positive and negative frequency terms, leading to Schrodinger's alarming phenomena of particle creation in the early universe. And this is sort of the last warm-up slide. You can define the co-moving number density of particles at late times as an integral over the modes of beta of k squared. So it's just a Bogoliubov coefficient, a Bogoliubov transformation going from the initial de Sitter phase to the final Minkowski phase. So the program is to assume an initial adiabatic conditions that are true for inflation and solve the wave equation with initial conditions alpha squared equal to 1 and beta squared equal to 0. Then you will assume late time adiabatic conditions, which are true for FRW, and calculate beta k squared in terms of the frequencies and the wave, the mode function and its derivative. And this is a graph for conformally coupled scalars of how beta k squared grows with time. You start off at eta equal to minus infinity in the de Sitter phase, so inflation happens way out there. Then inflation ends, and around the end of inflation for conformally coupled scalars, beta of k squared oscillates and eventually going to a constant, but the constant that beta k squared goes to is not 0, and that corresponds to particle production. So this is sort of a picture of how we imagine things to happen. At very small length scale, they're a stringy thing, strings, brains, what have you. And at some scale lambda sub s, then this is converted to 10-dimensional supergravity plus other fields. And then there is a scale of, associated with the Kaluza-Klein to get to 4-dimension supergravity. And then supergravity is broken, and we end up with what we normally use in cosmology. So is there a swamp for 4-dimensional supergravity models? So if you look at 4-dimensional EFTs, some of them will be in the swampland if you have infinite particle creation, and some will be in the landscape. And there's only these particles, the models that are in the landscape that are candidate models. So using gravitational particle production, we're going to try to see what the landscape is of the n equal 1, d equal to 4 supergravity. So here is our statement of the Gravitino swampland conjecture. And the statement is, in all 4-dimensional effective field theories that are low energy limits of quantum gravity, at all points in moduli space and for all initial conditions, the sound speed of the gravitinos must be non-vanishing. So if you have a field that has vanishing sound speed during inflation, you will produce a large number of them. In general, a theory of many interacting fields, the scalar sound speed CS should be understood as the determinant of the matrix of sound speeds of all fields kinematically coupled to the gravitino. And I believe Dudas will talk about this, and with mass below the UV cutoff. And there still may be issues for slow but not stopped gravitinos. If VS squared is less than 1, it could still be an important issue, even if it's not equal to 0. So that is the statement of the swampland, Gravitino swampland conjecture. And so another way of saying it is that supergravity EFTs with lonely constant mass gravitinos must have the mass smaller than the expansion rate. I have that backwards, must have the mass larger than HE. So there are implications for observations and experiment. If you assume a lonely constant mass gravitino in conventional thermal history, the mass must be larger than HE. This implies two things. One, if a gravitino is observed at terrestrial particle collider with a mass smaller than a TeV, then the cosmological experiments will never observe B-mode polarization of the CMB generated by gravitational waves, because the mass has to, HE has to be smaller than the mass. So if you see a gravitino at a terrestrial particle collider, you're saying that the mass, that the expansion rate during inflation must be smaller than the mass, and smaller than a TeV would be pretty hard to arrange. On the other hand, if B-mode polarization from primordial gravitational waves is observed, then collider experiments will never see a gravitino. So with this assumption of a lonely constant mass gravitino in conventional thermal history, it has an impact on observation and experiment. So that's the conclusion of my talk on the gravitino swampland conjecture at the 2021 workshop. And I will tell you, want to remind you again of my collaborators, Andrew Long and Evan McDonald. And what we're working on now is the gravitational production of massive spin-2 fields. And so in the 2022 workshop, I will come and talk about the standard, about the gravitational particle production of massive spin-2 fields. And that's my title for next year.
So this time we have with us Alex Pomarol. Please tell us first briefly, what's the main subject of the talk you gave in the workshop?
Okay, my talk on the workshop was about instantons, small instantons, that in few words, this is a calculation of an amplitude that usually you cannot get from perturbative methods. Okay, so it's a non-perturbative configuration that that tells you something usually that is non-trivial because can break some symmetries that at the perturbative level are not broken. Okay, and I was interested more in this configuration are called instanton. I was more interested when they are very small. Okay, so they are very sensitive to what we have at very high energies. So because my talk was inspired for looking for beyond the standard model physics, my calculation of this instanton was in the limit in which very high energy, I was considering to have probably that some extra dimension opens up, okay, and to understand what happened with this configuration when you have these extra dimensions, okay. So there was a calculation of how big is this amplitude and if it can affect, for example, something very important like the axion mass.
About Corfu, do you have any experience from the Corfu Institute and some views on the workshop standard model beyond that you took part?
It's a pity this year I couldn't go. I mean, I've been in Corfu.
We all understand, yes, of course.
Yeah, I've been in Corfu before 2 times. I love it to go. So it's a very nice place to visit because combine 2 things. It's a nice place where it's beautiful to be and it's a very good people there, very good researchers. So when you have this combination, this is a perfect place to go. So when I am invited, I usually go. So this time I was invited, but the situation of the pandemic was very bad. I couldn't go. Nevertheless, I followed the talks and I was able to ask questions and this thing. So this is a good thing because it's a little bit of mixture of all types of beyond the standard model physics. So you can get a little bit of knowing from neutrino physics, cosmology, dark matter, collider physics. So it's a little bit of everything, and it's carried out by very, very good people. So it was wonderful, yes.
So, and the last thing is suggestion to young scientists starting research now.
Well, I mean, research is a beautiful thing. I mean, it's difficult to convince. It's something when you like it or not, that kind of, okay? I mean, I think I understand a lot of people don't want to get this road because sometimes it's a lot of effort, but I tell you that you will compensate this effort in the long run. I'm convinced of that, okay? So I understand at the beginning you will think the situation is not easy, you have to go abroad, but at the long run, I mean, this is a beautiful job. I mean, you get every morning and you can do whatever you like. You start thinking about your own projects, and this is a beautiful sensation. Okay, it's not like going to an office where you're bored. I never bore when I do research because if I bore, I move to something else. So I think in the long run, okay. So I understand at the beginning it could be tough, but in the long run, it's wonderful. Yes.
Okay, thank you very much, Alex.
Okay, so I start. Okay, so okay, thank you for the invitation. It's a pity I cannot be there in Corfu, the beautiful Corfu. Okay, I'm sure you're having a lot of fun, but I couldn't make it. The situation, COVID situation was not very good here in Barcelona, so that was the pity. Okay, my intention here is to talk about the axion mass, okay, and to understand if we can get contribution from the UV physics. Okay, so the axion solution to the Stone-Shipy problem, of course, is we like it because it's a very neat solution. And now on the top of it is a very interesting thing that, and this is what we claim usually, is that it's fully determined by the infrared physics. Okay, apart from the decay constant of the axion, the rest depends on properties that we can extract from QCD. Okay, and that's what it makes very a very predictive theory in the order of getting what is the dark matter abundance, or to understand where we have to look for this action, okay? So the range of experimental searches, okay? So it's a very crucial, important thing that the axion mass and the physics of the actions is determined mostly from QCD. So we can calculate. Nevertheless, my question here is how robust is this? Or in other way, how easy or difficult is to get the axion mass or contribution to the axion mass from UV physics, okay? Of course, what I want to say, it's easy to give contribution from UV physics. You break the Pechequin symmetry and you get contribution, but here, this is not my purpose, okay? My purpose is to see if there can be contributions without, of course, spoiling the action solution to the strong CP problem, okay? And this is what it means. It means that in order not to spoil the strong CP problem, the only source of breaking of the Pechequin symmetry should come from the anomaly, okay? So it means that the only contribution from the action should come from the instantons, okay? So we have to understand if the instanton is dominated by infrared physics or from UV physics, okay? In order to do this, let me recall how it goes, the contribution from the instantons. We'll go back to the calculation of Toft in '76. Okay, let me start with pure Young-Mills. And we can calculate the vacuum to vacuum instanton amplitude, okay, doing it in a semi-classical approximation. Okay, we calculate the instanton, and at the classical level, we get the famous exponential suppression e to the minus 2 pi over alpha strong. Okay, and at next to leading order, we have to integrate over fluctuations around the instantons. Okay, and this is what Toft did in '76. And now is where you get, let me move this. This is where you get that the contribution comes from integrating over all the instanton sizes, okay, from a small instanton to large instanton. Okay, and the important point here is that this is weighed by exponential factor, but when you include the fluctuation, evaluated at the size of the instanton, of course. The coupling should be evaluated some physical scale. The only physical scale in the problem is the size of the instanton, okay? So this automatically tells you that this integral will be dominated where the alpha strong is the largest, okay, or the suppression is the smallest. And this is, of course, in the case of a Young-Mills theory, in the infrared, okay? So the coupling grows towards the infrared, becomes large there, and now we expect from this calculation that the large instantons, those at the lambda QCD, will dominate this integral, okay? And small instantons, okay, instanton depending on the UV physics, will be highly suppressed, okay? Okay, this is from, without including fermion. When you include fermion, of course, we know that the anomaly, the anomalies related with the chiral anomaly. And now, in some sense, the process we were looking before, the instanton, in some sense, is a contribution to the chiral breaking. So in some sense, now the process is not just the one before, because we are producing now a chiral charge. So in some sense, we are producing fermions. Now the process is this one, and now to get a contribution to the vacuum, now we have to close the fermion lines. Of course, we can close them by inserting the mass of the fermions, but now it is clear that on dimensional grounds, this will be proportional to the mass of the whole fermion divided by some scale, and of course, again, the scale, what is the scale? The scale is the scale of the size of the instanton, 1 over the size of the instanton. So for a small instanton, meaning large lambda, again, this is suppressed, okay? So there is two suppression for small instantons, for UV instantons, just coming from these two factors. The coupling is usually in the UV smaller, and now you have to pay a price of masses over the lambda that is related with 1 over the size. A complicated model building options, but we wanted to understand if there could be a simple way to get this instanton, small instanton contribution to be large, okay, apart from this one that I was saying. We considered with my colleagues the idea of, I don't know, going up into the high energy, you enter into an extra dimension. Okay, we know this can happen, for example, in string theory when you get close to the Planck scale. Okay, if it's open up an extra dimension, we were thinking what could be the contribution. Of course, we know that that there are plenty of Kaluza-Klein state when you enter into the extra dimension. So if the instantons are small in size, what is the contribution that you get there? Okay, now the calculation that we have to do in some sense is straightforward. It's just a repetition of the calculation that Todd did long ago. Okay, we have to integrate over the fluctuations. Okay, now in this case they are the 5-dimensional fluctuations, so integrating over all the Kaluza-Klein. Okay, now the instanton in 5 dimension, we were just because we have to calculate fluctuation around the classical solution. The classical solution we consider in 5 dimension, it was a simple uplifting of 4-dimension instanton. So in an instanton depend on the extra, that does not depend on the extra dimension. It's the 4-dimensional instanton at which we uplifted to an extra dimensions. Okay, with the 5th extra components being 0. Okay, so this is of course a solution of our Jamil's equation in 5D. Okay, and now we calculated this fluctuation. Okay, now the calculation, I mean, a priori is straightforward. I mean, we follow the usual process, and now this is the solution. What we get is, so this is what we want to comment. The first thing we get is the famous 2 pi of alpha strong, but now alpha is evaluated at the compactification scale. No, it's not evaluated at the size of the instanton. But now we were getting a factor here, okay, that was interesting, was growing with the size of the extra dimension over the size of the instanton. Okay, so if the instanton becomes smaller than the extra dimension, this is a power law correction. Okay, times a function that we can calculate it. Here is the solution that goes to a constant for large values of r over rho. That goes to a constant like something like 1/3. So this is a third, 3 times the third. So this is more or less a factor 1. Okay, and this plus some log corrections. And this is in content with what we get in 4 dimension. 4 dimension already told you to show that the contribution was nicely resummed by evaluating 2 pi of alpha strong at the size of the instanton. Here we see is evaluated at the compactification scale plus some power law corrections. Okay, and interesting thing is the sign. Okay, surprisingly, we're expecting that the sign had to be positive because in Yang-Mills theories, as I was saying, in 4 dimension, for example, the contribution becomes smaller, the coupling becomes smaller and smaller, as we go to smaller and smaller instanton. Okay, however, here we see that this is making so the action becomes larger and larger. Okay, alpha becomes smaller here in 4D, so the action is larger, so this exponential suppression becomes more suppressed. Okay, but here we get that the minus sign. So it means that the action as we enter into this extra dimension compensate a little bit the factor 2 pi over alpha strong. Okay, and this is was surprising. We don't understand the sign. It's coming from the calculation, but probably I don't know. We could have expected a different thing. Now, what does it mean? It means that now if I go to the amplitude contribution of the instanton vacuum to vacuum amplitude contribution, the exponential factor, as I was saying, if I draw this exponential factor as a function of the size of the instanton, 1 over the size of the instanton in GeV, okay, I see that of course, that we were saying the coupling becomes smaller, so the exponential factor become much smaller. But when we enter into the extra dimension, we have this extra power law correction that changes the sign and makes the instanton contribution to increase. Of course, the size of the instanton becomes smaller and smaller, and we enter into the extra dimension. There is a point we have to be careful. 5-dimensional theories are non-renormalizable. There is a UV cutoff. You can estimate it where the loops are important. Okay, so this our semi-classical calculation doesn't make any sense. So we have to stop at some point. Okay, and this is can be estimated to be something like of order 1 over the alpha strong. Okay, so we see that there is a contribution here that you can have when you enter into the extra dimension, but you cannot get too much into it, otherwise you hit the cutoff. Okay, now this is the amplitude contribution, the vacuum amplitude contribution from the instanton, now including the action to calculate the action mass, we just shift because the action coupled to the G dual, the action is shifted by S to the minus A over the decay constant of the action. Okay, and now we can calculate the contribution to the action mass. Here the solution. Okay, this is the action mass contribution normalized to the contribution you get from QCD. Okay, this is what we know from QCD, and this is what we usually rely our calculations. And now, of course, we want to see when the contribution is larger than 1. Okay, when this UV instanton, this small size instanton for the compactification scale becomes important, and this is plotted as a function of this compactification scale. Okay, so here, of course, now depends. Go back to here. Depends how much you see. This is an integral over all size of instanton. Depends how much you get into how much we integrate here. Okay, we get too much into the extra dimension, into the extra dimension, we will hit the cutoff. Okay, so here are different lines depending how much we integrate over these small instantons. And of course, if we get too much into it, we can get, of course, a strongly coupled regime, of course, where the contributions are very large, but you cannot rely this calculation. And we can see that we can still rely if we stay along something like an order of magnitude, probably almost an order of magnitude below the cutoff. And we see that even in the case, if the extra dimension is large, it's close to, I don't know, the Planck scale, still you can get some contribution 2-3 order of magnitude above QCD. Of course, this is as I say, you have to be careful because, of course, we're very close to the cutoff. Okay, of course, if you don't get close to the cutoff, this power law correction cannot be important. Okay, so you have to be a little bit aware that there is this uncertainty that the way we estimated the UV cutoff. Okay, but at least looks like yes, you could do at least in some region where you stay an order of magnitude of this cutoff. Looks like safe, and you could have this contribution to be important enough to give to the action UV contribution. Okay, so let me close this thing and conclude. Okay, so there is the possibility to give. My point is the possibility to give contribution from the UV, but this have to come from a small instanton. You don't want to spoil the strong CP problem solution that the action give you, and the only solution you have is to enhance, of course, this small instanton by enhancing the gauge coupling. In the extra dimension, you could do it, but you have to be aware, you have to be very close to the non-perturbative limit to get a contribution to the action mass that overcome the QCD contribution. And surprisingly, when you go to ADS 5, even it looks like the right place to look for this thing because you have this log enhancement of the coupling. Seems to be that this is suppressed. We didn't find a UV localized instanton that will give you an action, a smaller action and a higher contribution to the instanton amplitude. Okay, thank you.